let's get started again with our talk before the lunch break. This will be presented by Ben Tanner. Come on up, Ben, Stetson University. The title of Ben's talk is Organic Sediment Accumulation Within Spring Runs Associated with the St. Johns, Santa Fe, and Suwannee Rivers. Thanks, Ben.
Yeah. Thank you. I appreciate being here. I wanted to thank the Osceola Research Institute for having me, and especially Jim. I got to know him back in the 90s when I was at Florida State and thought I was going to do underwater archaeology, and then kind of life happened and I drifted off into a different direction. But it's been nice of Jim to kind of try to pull me back kind of into the fold since I've been back in Florida. Let's see here. So I'm going to talk a little bit about a project I started when I did come back to Florida back in 2016. I was in a couple of other places before that, but a colleague of mine, Kirsten Work, who's a biologist who's been working in spring runs kind of for a long time, I want to acknowledge her, was the one that kind of got me into this project to start with because of some questions that she had that dealt with Florida and Florida Springs and some different threats that they were facing. So basically, we know that Florida springs are abundant. I don't have to tell this crowd that. I mean, we get to enjoy all the springs that we've got around in this area, and of course we find them throughout the state. But I think we all know that Florida springs are also threatened in different ways. Not all springs, certainly, and some face different threats than others, but in some places we're dealing with threats related to water quantity. In other places we're dealing with threats related to water quality. And of course we have things like invasives that we have to deal with in our springs and our spring systems as well. And of course in some springs and spring runs we're dealing with multiple threats, at the same time. So one thing that she was thinking about at the time, and this is kind of when I arrived back in Florida, was that some springs and spring runs have shifted from a macrophyte or kind of a higher plant dominance to algal dominance, and was kind of thinking about that and what some of the reasons might be that we're driving this change in the springs. Of course, one obvious potential contributor to that might be things like nutrients or nutrient pollution that could lead to those kinds of changes. But that didn't seem to explain the shift in all of the springs that she had been looking at. So one question that she had was the question of potentially organic sediments or organic rich sediments as a potential source of nutrients that was present there in the spring runs. Kind of, you could probably think about that maybe in the way that you might think about your garden and adding organic sediments there and getting things to grow. So could that be a source of nutrients to the spring run? So that's kind of where I came into the picture, because over the years I worked in different wetland environments, and I like to take soil cores and interpret them for all kinds of different interesting things that can happen back in time. So I said, well, why don't we go try to take some sediment cores in spring runs and see what we get, and the idea being, if you had recent organic accumulation in a lot of the spring run, maybe then you could hypothesize that could be a reason that we're getting some extra nutrient load, and maybe that's contributing in some way to some of the algal proliferation and that kind of thing. Whereas if the organic sediments have been accumulating for a long time, maybe that would suggest that there's not a recent contribution from that particular source. So that was a very basic kind of fundamental question, and that's really what got me into the spring work and the spring research. It did take me long to realize that this is a really nice setting to work in. I'm used to getting buried in mud and salt marsh and mangrove systems, and you finish your field day and you're covered in mud and you're hot and sweaty. And spring runs are so nice to work in. If you get mud on, you jump in the water and you're nice and clean, and it gets rid of all the sweat, and so these were just really pleasant places to work. So it didn't take me very long to kind of latch right onto this as a nice place to do some scientific study. But I want to talk about some of the work that we originally did, and this is what I think Jim asked me to talk about here. We had visited 15 different sites that are on the, that are along the St. John's. These are different spring runs along the St. John's, and then the Suwannee and also Santa Fe rivers, where she had done previous work and was looking at things like fish populations and nutrient levels and this kind of thing. And so what we set out to do is establish transects kind of along the edges of these spring runs. And we would go along and probe every 3 meters along these transects and collect the sediments. And essentially what we were looking for is the deepest organic deposits or organic rich deposits that we could find. And once we did, we would go back and take more detailed cores at those spots so that we could bring them back to the lab and work up at least a really basic record of what we were finding there. So what we went for to capture variability is maximum organic accumulation along the transects that we laid out, as well as maximum spacing between the different spots, because we did want to capture a little bit of variability. But this was a pretty coarse survey at this point. We were just trying to get an idea of how much organic sediment was there, how deep it was, and how old it was. So when we took the cores, we sampled the top, the middle, and the bottom, just to get an idea of what kinds of changes in a rough way we might see down core and how much organic sediment was there. And then for the bottom samples, kind of the idea, of course, being as you go deeper down, you're getting older and older and older sediment. So for the bottom samples, getting radiocarbon dates or carbon dating them so we could get an idea of the maximum age that was represented in those different cores and the different samples. So that's what we did. So again, I've already mentioned the field sites, and what I want to go through kind of one by one is describe basically what we saw from this study at each particular field site, and I think it'll get more interesting as we go along from spring to spring, because I'm going to go along in order of maximum age of the deposit that we found at each site. So a couple of springs we sampled, when we radiocarbon dated the bottom deposits, we actually got modern ages returned. So in these cases, the sediments hadn't been accumulating for very long, and the deposition of the organics, at least in the locations that we happened to sample, likely began within the last 300 years. So what I'm going to show you on these graphs is a pretty simple plot of just the depth of the deposit. And I know all my data points are up here on this graph. There's a reason for that. That's because we're about to look at 15 of these. Don't worry, we're going to go through them pretty fast. But I wanted to keep the axes the same on all the graphs so that you can see how the deposits are different in the spring run. If you're seeing data points kind of up here in this corner, what it means is there's not a lot of organic deposition there. Okay, so the cores aren't very deep, basically. I'm sorry. That's depth on this axis. So if we're up here, kind of up higher, that means we couldn't go very far before we hit bottom. We hit refusal, we call that. And that could be different kinds of things. It might be bedrock. It might be some layer that you simply can't get through. And as we go this direction, what we're looking at on this axis is called loss on ignition. Basically, we take the sample and we burn it in a muffle furnace, and we weigh it before and after, and we see how much was lost, how much weight was lost. Pretty simple measurement, but it gives you an idea of how much organic material is in the core, because that's going to burn off when you combust it at 500 degrees Celsius. So when we go in this direction, that's kind of the direction I'm looking for if I'm interested in deep organic sediments that I might be able to come back and look at later for all kinds of interesting things, like looking at how environments have changed through time. But what I'm looking for there is deeper sediments and also more organic rich sediments. And if they're old, that's really nice too, because that means you can get a record that goes back further. So in this case, Troy Spring wasn't kind of as interesting to me for this because our data points kind of clump up in this corner, and we got a modern date for the deposits really that weren't that deep. Same was true for Rock Spring. So you can see on the map where these different springs are. Rock Spring is a wonderful spring. It's a beautiful site. I love to take my classes here. Wonderful place to see karst topography. You've got water that issues directly out of a cave here. So really neat place. It turns out it's not a good place to go and take sediment course because the deposits weren't very deep. They weren't very organic rich. And we didn't get a very old age, so we got a modern radiocarbon date from there as well. Volusia Blue Spring, so this is Blue Spring in Volusia County, and a great place to go see manatees during the right time of year if you've never been there before. If you go in the winter, sometimes you can see over 100 manatees in the spring run. But we found that the sediments there were pretty mineral rich in the spring run. We weren't able to get very deep cores there, but all of a sudden we're on the page, at least in terms of radiocarbon dates. We returned an age there that was just kind of barely where you can get an age with radiocarbon dating. Is about 300 calibrated years before present. Alexander Spring, this is a spring run that feeds into the St. Johns River. We got really high organic material in some places. Still, our cores weren't very deep, but we're starting to get ages that are a little older here. We got a 1,500, almost 1,500-year-old age for our basal date. It turns out that in some of these spring runs there are probably deeper other types of deposits in different places. I know I've been back there since then with a colleague of mine at Stetson, Jason Evans, further down the spring run. And I've taken a sediment core that is over 2 meters deep of organic material. So I know in some of these places there are deposits defined that are interesting in other parts of the spring run, but back when we did the study where we happened to sample, they weren't there. This is Silver Glen. This also feeds into the St. Johns River. A lot of potential for disturbance in this particular location because it's a place where people like to pull up into their boat, go swimming in the National Forest recreation area in the spring and hang out kind of right by where the line is out in the water and party. So we sampled here. We got an age of getting close to 1,500 years. Actually, quite a bit of organic material in the core, and they were fairly deep. It went down to about a meter in depth. This is Gemini. This is a county park that feeds into basically the St. Johns River, ultimately. But again, not a lot of organic accumulation there, not very deep cores, but we did get an age that's a little older there. So this is Hart Spring. This is in a different area. This one feeds into the Suwannee River. And you kind of know what you're looking at. We got about a meter. We got some cores that had kind of richer organic material in them, and our dates are starting to get older here. Hart Spring, which is not too far away from Otter, got slightly older ages there, deeper core, fairly decent amount of organic material there. Both these springs actually turned out to be fairly interesting for me because the cores showed that there was a lot of environmental change in the area with different facies that were represented in the deposits. So I was interested in kind of following up on those and looking at them later, but that's what we got in this initial study. This is Otter Spring. So this is also feeds into the Suwannee River. And again, we're getting kind of older ages here, organic rich deposits, down about a meter in depth for the organic sediments that we were able to collect. Again, going older in age here, this is Manatee Spring. You would expect that as you're getting older, you might be finding deeper deposits. That's what we got here, and pretty organic rich. This is De Leon, about 6,600 years calibrated before present, about a meter of accumulation there, and pretty organic rich sediments there as well. So this isn't too far from my neck of the woods. This is probably the closest spring that we've got. where I work to Stetson University, but ultimately it feeds into the St. John River system as well. Salt Spring, pretty interesting, kind of organic rich sediments we found there, getting pretty old here now, getting towards the earlier part of the Holocene, and we got pretty deep cores there and pretty organic rich sediments kind of throughout. Once we hit the Santa Fe, things got pretty interesting. Around Ichituckney, where we were sampling, not necessarily deep deposits, but we got a pretty impressive radiocarbon date from our basal deposits. So now we're out of the Holocene here. That was Ichituckney. Okay, yeah, Gilchrist Blue. We got an even older age, and we went back and dated that several more different ways with different types of macrofossils as well. But we've got about 1.5 meters of sediment, pretty organic rich, and as you can see here, it was pretty old. My personal favorite was Wekiwa Spring, it's Wekiwa River. Really organic rich deposits. This hits everything I was talking about. We've got organic rich deposits. We've got a really old basal radiocarbon date here, a little more than 8,500 calibrated years before the present. And we've got really deep deposits. So I want to mention that I only brought, this is 300 centimeters or 3 meters. That's about 10 feet. Okay, so if you imagine a regulation basketball goal, that's how much organic sediment we had below that. And I only brought 3 meters of core barrel, so it actually goes down further than that. So in this location, I think you actually have the potential to get a really interesting record there that you could look at changing environments back, pretty far back in time. So we were able to publish this work in 2020. And I'm not going to go through all these again, but these are the different radiocarbon dates that we ran for this study. When we started getting really old, kind of deeper deposits, we started dating plant macrofossils at some of these springs that we were a little more interested in. And what they did was confirm that some of our original ages that we used on bulk sediments were actually pretty valid, and the macrofossils that we were pulling out were returning similar ages. So this sums up what I just went through, so I won't dwell on it, but the interesting sites for us, we've got age here, so these are older. This is of our basal deposits, and then we've got the depth of the organic sedimentation that we were looking at for the different sites. So when you see both those bars that are high, those turned out to be interesting sites for me personally. And Wekiwa Spring especially, I thought was especially worthwhile to kind of return to and visit again because of its long record that goes kind of far back in time. I won't dwell on this either. You all have already looked at a lot of the data I went through kind of slide by slide, but this just shows the amount of organic material that we found in the top, middle, and bottom of each core for those different sites. I really don't know if I want to dwell on this, but we also looked at isotopes and carbon to nitrogen ratios. So these are different versions of carbon, essentially. Carbon is carbon, the element. Is going to participate in different ways in things that carbon likes to do. It might form carbonates like calcite and become part of limestone. It might become part of organic matter. But because you have different isotopes or different atomic masses, basically different atoms of carbon can weigh a little bit different mass, you might change, like a phase change. Some carbon might diffuse quicker, for example, through the stomata of a leaf than other types of carbon, and that can tell you different things about the natural world. So we like to look at stable isotopes to tell us different things about past environments. But looking at all the samples that we looked at for that study, Basically, most of them were falling in the range of what you might expect to find around the spring run. C3 plants, so these are plants that you might find as floating aquatic vegetation. You might find as the trees and shrubs or whatever that exist along the stream bank. But basically, most of the organic matter that we found as part of that study, all the samples that we took, kind of fell within the range that you would expect for things that were growing kind of in or around the spring run itself. So our conclusion for that study is that many Florida spring runs do contain abundant organic rich sediment that's been accumulating in some cases for thousands of years. We didn't have the kind of original question that we were asking in this study. We didn't have much evidence for the recent onset of organic accumulation as a source of nutrients because organics have been accumulating at a lot of these spring runs kind of for a long period of time. And it seems like a few of these spring runs, whether they were active in flowing or whether they're just wet, is maybe it's a question that's hard to answer from our study. But we've at least got evidence that some were wet well before Holocene sea level stability because we've got a lot of organic material that's accumulated there. And you really need kind of anaerobic conditions to accumulate that kind of organic material and not have it break down. So because we've got sites like Wekiwa Spring where we got 3 meters of this stuff and it's been accumulating, it looks like, for about 18,000 years or so, that suggests that at least the site was wet over long periods of time, whether the spring was flowing or not. And so for me, this was exciting, even though it turned out these probably wasn't acting as like a new source of nutrients for the spring run. For me, it was kind of more exciting because it looked like at a lot of these places you had the potential for paleo-environmental reconstruction. Basically looking at the cores and trying to make interpretations of how the environment's changed through time. Let's see. Kind of the question, I don't know if I want to get into this, and I know somebody showed a slide similar to this yesterday, but this kind of gets to this point here, that these spring runs, at least some of them, may have been wet before Holocene sea level stability. What I mean by that is at the end of the last glacial, as all the ice was melting, especially in the northern hemisphere, that ice basically equals sea level rise. So Florida went from being really, really big, kind of more to the shape that we've got now. So sea level rise moved fairly rapidly, but began to slow down and stabilize about 8,000 years ago. The reason I mention that, because the idea is when your water is coming up, it's probably going to push your water tables up, if that makes sense, and that's probably a good time where springs, a lot of the springs we've got around the state today may have begun to flow. Okay, on to Wekiwa Spring, where we did some more detail work. This is what my field crew likes to do at the end of the day. So when I let them go, they all go jump in the spring run here. Just kidding, but there's a lot of people there. So it's a pretty crowded spring, but when you get down into the spring run, it's a little less busy. Just to remind you, this was a site that was interesting to me because kind of in our kind of core study, kind of looking at organic sediment accumulation in a lot of spring runs, we found really deep deposits there, and they were organic rich and they were really old. So I thought that this was a kind of a prime candidate to go revisit and learn a little bit more about that spring. So here's that site. It's way down. Ultimately, it feeds into the St. Johns River, the Wekiwa River does. So we did more work there. Again, we pulled about 3 meters of sediment from that spring, really organic, rich. We didn't go below that, but you could. And we radiocarbon dated multiple depths down core, and we used different types of plant macrofossils for that. And it was a little sad for me because we got a radiocarbon date that was out of stratigraphic order, but it happens sometimes, so you just deal with it. So just for people that aren't used to looking at stuff like this, you expect as you go deeper that your ages get older and older because you have to have deposits there for the new deposits to form on top of. So that pattern is kind of preserved here, but when you go backwards here, you're getting deeper, but you're getting younger. So we call that a radiocarbon date that's out of stratigraphic order, and it can happen for different reasons. It might be disturbance, it might be a plant macrofossil that was resuspended and deposited in a different place that was older. There are a lot of different reasons why that could be. But anyway, that's a data point that was there that we just have to deal with. But we got, again, pretty old ages with this place that we revisited in Cord. And we got a record that goes from kind of toward the end of the Pleistocene here, kind of up into and through the Holocene. I probably won't go through all of these, but these are some of the different things we found, and I'll point out one thing that's interesting to me. We found first that there was a lot of organic material all the way down core. That's perhaps not a big surprise, a little less towards the bottom of the core. I'm going to skip ahead to here. I've got a colleague at Stetson, Kirsten Work, that counted area of shell. So these were gastropods that were present in the core sample, and we can see that we hit a pretty coarse shell layer that was down here at the bottom. It's relatively organic rich still above 5% organics, but there was a lot of shell there that represented different types of gastropods there as well. This is a part of the sand fraction. It's where we actually caught most of the sand in the 120 mesh sieve. And a lot of that fraction is probably from shell. But I want to point out this big spike up toward the surface where we don't really have shell. So this represents quartz-rich sand. And we see it as we come into the modern time. And I think what that probably represents is a legacy of human use and disturbance and kind of stirring up the deposits that are present in the spring and a lot of the spring run and suspending them and sending them to our core location. That would take further work to demonstrate conclusively, but I suspect that's probably a good reason why we're getting this first really big sand spike that we see over the course of 15,000 years here and right up toward the top of the core. I want to speak very briefly about where this work has led, I think in a very interesting direction, and I know I have to make it quick here because I'm starting to run short on time, but with my colleague Jason Evans, who's been working on this for a long time, we've started to look at water lettuce as a native plant in Florida. So anybody that's worked around in springs has seen this stuff before, I'm sure, in the spring runs. And even now, I just downloaded this the other day, and we've gone from the 2019 list of invasive species recently to the 2025. And water lettuce, or Pistia stratiotus, is listed as an invasive species. My colleague Jason Evans pointed out, this is one piece of evidence he pointed out in a paper, but that William Bartram saw it in 1765 and 1774 in Florida. Maybe the Spanish brought it in or something before that. But he published a paper back in 2013 where he suggested that water lettuce, for a variety of reasons, including that evidence, was actually a native plant. So when we got together and he saw kind of what we were doing with some of the cores, we began to wonder if these were ideal locations to go look for seeds of the water lettuce down in core deposits, because if you could find them, that of course would suggest water lettuce had been around in Florida for a long time. Thank you. I'll go through this fast, just a few more minutes here. So that's what we did. Just to go through this very briefly, the first thing we did is actually look at surface sediments in places where water lettuce was abundant to see how many seeds you might expect to find where water lettuce is abundant. So we ended up looking at quite a bit of sediment. 7,676 cubic centimeters, and we found 3 pistia seeds, or water lettuce seeds. So we know that water lettuce seeds aren't very abundant even where water lettuce is present. Probably don't have time to get into this. But then we went and we looked at sediment cores, with the idea being that we would look down core to look for water lettuce seeds and hopefully find some old ones and then radiocarbon date them. So we ended up looking at quite a bit of sediment. We actually found about the same concentration of seeds in the core sediment that we did in the surface deposits. Most of them were actually higher up in cores, but we actually found some in deeper deposits as well that we tried to radiocarbon date, and we didn't get old ages for them. They returned modern ages. So it's kind of like finding a needle in a haystack, and we probably just haven't found old seeds yet. But from a Quillen study on diatoms at Lake Annie, which is on the Lake Wales Ridge down in South Florida, they kind of casually mentioned that pistia seeds were found in core samples there that were taken back in the 1990s. So just to kind of orient you where we are in Florida, this is Lake Tulane, which I'm going to talk just a little bit about. And Lake Annie is further north from there, and some of you may know of Lake Annie because it represents one of our probably best paleo-environmental records that's been found in Florida. It goes back to about 60,000 years old. Very detailed pollen record and other types of records have come from there. But we were very interested because the Lake Tulane work was never actually. I'm sorry, I'm swapping these sites. I'm standing here looking at Lake Tulane. We were looking at the Lake Annie deposits, and yeah, the Lake Tulane deposits were the ones that were really old, 60,000 years. This work was never published. So we went back and contacted the folks who took those cores, Eric Grimm and George Jacobson, and they were very interested in publishing that work. So it turns out back in the 90s, they had actually, this is a core that they worked up. We're looking at age here on this axis and depth on this axis, but they had really deep deposits in the lake. And this sample here, these are radiocarbon dates, actually represents water lettuce seeds that they dated in that study. And so it turns out that they were about 13,000 years old. And they've got pictures of those. So these were SEM images of those seeds. So that was pretty cool. So we worked with them. We recognized the significance. Actually, I think even back then they recognized the significance of that, but they went on to publishing the Lake Tulane work and never published the Lake Annie work. We just put that out about a year ago with them. And so it's also a pretty neat pollen record that goes back to about 15,000 years old, but these are the water lettuce seeds right here. Recent genetic work, actually this came out before we published that Lake Annie record, but it's confirmed that genetic evidence suggests there's a native variety of water lettuce in Florida, that there are invasive varieties as well, but there's a native varieties of water lettuce here too, at least one, which is kind of cool. So the reason I wanted to present this briefly to you all is because I know a lot of you all are looking at spring deposits, and if you ever find these things, I'd like to know about it. And that's all I've got.